here we are. Once again, this time we are going to begin our adventure into the world of modern physics. Modern physics. Everything up till now has been considered what we call classical physics. So if we start with Newton, just as a benchmark, these are some of the highlights, right? We have Newton and all of his laws of motion, his law of gravity, and so on. Then a little bit later, we see the work of people like Ørsted and Faraday in their dealings with electricity and Ampere. And what was happening was a drastic change in the way people thought about the world. Ampere. And then, of course, we'll finish off with Maxwell here. What we've seen is that Newton thought of the world in a certain way, right? In fact, let me just put a little bracket here and put classical physics. So, originally, Newton actually thought about light, and he did a lot of work with light. And he did some cool things with prisms, and he envisioned that light was made up of some tiny little balls of light, particles of light that somehow streamed around and bounced off of things, mirrors, and gave us all the effects that we noticed. But that was quickly changed over time when people started to notice that a stream of particles couldn't do the things that light was doing. And we have seen that light can be demonstrated. I guess I could have also thrown in Young with his double slit experiments in that list. But we have seen that this wasn't the way they were looking at the world. They were looking at the world with waves. Waves were the thing. Waves are a form of classical physics. We know how they work. We can write all kinds of equations for waves in the water, waves in the air, pressure waves, compression waves, longitudinal waves, and transverse waves. We've got waves down pat. And everybody was using waves. And so Newton's original idea got transferred over a few hundred years into waves are the thing. In fact, it culminates when Maxwell derived equations, Maxwell's equations for light, are based on waves. And it seemed like everything was working out wonderful. So now light was electromagnetic waves that travel in sort of a two-dimensional way. You see in this picture, right? A magnetic and electric vibrations at right angles to each other. And at this point, people really started to think that, hey, we are done. Physics is over. We have figured out everything. In fact, a guy by the name of Kelvin, Lord Kelvin, who was a famous scientist around that time, made the remark that, we've learned everything. We're done. All he said we have to do now is just improve our accuracy, but all of our theories seem to explain everything that we can observe in the universe. But he was drastically wrong. And the reason that he was drastically wrong is because up until this point, we had a very limited way of viewing the universe. Originally, humans could only view or experience the universe with their five senses, what they could see, smell, taste, touch, and so on. And we did a pretty good job of using these senses to interpret the world. But around the turn of the century, we were also entering into a time where the Industrial Revolution was going on, there was technology happening, and people were able to discover that there was more to the world than our senses actually led us to believe. And that's where the problems began. There were there's four major problems that began to be observed. And we'll start out by highlighting what those major problems were. Major problems with classical physics. People were doing cool experiments. People were firing electrons and beams at slits in screens, and they were using light to move things around, and reflecting light off of metals to produce energy, and all these things were very interesting things that they were not explainable by classical physics. In fact, they were just downright wrong when we tried to explain them with classical physics. So, the first problem was that according to classical wave theory and the way waves work, if we use all of our math, tells us that energy can be of any value. In math, we say energy is continuous, like a mathematical function that can be anything, can be any value. But some people had shown us some things that proved that this was not true. So experiments showed this was not the case. And we'll talk about some of these experiments in just a minute. Now remember that science is all about building models to describe our universe and what we see or what we experience. If a model is created mathematically, it might be a wonderful model and it might be perfectly correct mathematically, but if it doesn't describe something in the universe that we can see, if we can't see it in action, then it's not any good to us as science. It's just an interesting mathematical idea. And so the key to science, what makes it different from everything else, is that when we come up with something cool, we have to make sure that that can be observed in the universe, or that it can be help explain some phenomenon. If it doesn't, it's no good to us. So our wave theory was great. It was explaining a lot of things. But now we notice some things it wasn't explaining, which tells us that our theory is either wrong or perhaps maybe just incomplete, and there's more to the story. That's what science is all about. So, wave theory was not working when we started looking at some of these new things. And I'm going to show you some of the examples of all this stuff a little bit in just a second. The second problem is that other experiments were showing that wavy things, like light, for instance, light was we thought we had it figured out. Light acts like a wave. It does, it diffracts, it interference, there's interference, there's diffraction, there's refraction, and of course we had Maxwell, he said, look at this, I can make waves of electromagnetic fields, and that's light, and everything is great. But wavy things like light were shown in some experiments to behave like particles. They behaved, like bowling balls rather than waves. Something was amiss. Behave like particles. And I'll show you some of the experiments that indicated that. A third thing that was being noticed is that the opposite was also true. Particle things, or particles, sometimes acted wavy. So things like electrons, which were thought of as little clunky particles, like little tiny marbles of some sort, they weren't behaving like marbles. They were behaving more like a wave. They were showing properties like interference. That doesn't make sense. How can a marble interfere? It doesn't really make sense. And so that was another problem that was suddenly popping up. And then the last major problem, and this one is a pretty big one. I like this one. Our model of the atom was, when we coupled it with the work of Maxwell, our model of the atom became impossible. Let's call it the impossible atom problem. And I'll explain that to you as well. But there are reasons why our atom couldn't work. The current model was flawed. Let's put it like that. Call it the impossible atom. Current atomic model was flawed. Now by flawed, Again, doesn't mean it's all wrong. Maybe a better word to say is it's incomplete. And that's the story of science all along. I mean, everything that Newton discovered or created or came up with isn't incorrect. It's just incomplete. And we've been adding to our science and tweaking everything. And it's kind of like adding more chapters to the book so that we get a better picture as we start to notice weird stuff. You know, think about poor Newton. He never heard of a black hole. He didn't understand anything like that. He didn't have the benefit of Einstein's theory of gravity to deal with. So in his world, he wrote his books based on what he saw, and they worked. But as people saw more things, the books had to be added to. So these are the 4 real problems. Let's take them one at a time, and we'll do them all in separate videos so that you don't get too overwhelmed by the thoughts. We're also going to try to avoid too much mathematics and think about concepts, a conceptual analysis of this, because the math is pretty heavy, especially if you only have high school math at your disposal. So, the first problem. Let's go back to problem number 1. Problem number 1, which basically said that wave theory doesn't explain everything. And the important thing to think about with wave theory is that waves are continuous waves, which means that they can have any value. And that was what was beginning to be the problem. There are 2 things we noticed that identified this problem. Well, at least these 2 things. These are the 2 big ones. Well, let's start with the first one, which is called the UV catastrophe. And it was called a catastrophe because it was basically showing that our model was breaking down. It wasn't accurate. It wasn't showing us the real world. And it was happening right around the point where ultraviolet light is in the spectrum. So it was called the UV catastrophe, or the big UV embarrassment, the big problem that we can't explain. In order to understand this, we have to learn a couple of things. We have to understand the concept of a black body. Okay? A black body is simply an object that reflects no energy. It reflects nothing. If light shines on it, the light is absorbed. If energy hits it in any way, the energy is absorbed. It reflects nothing. It absorbs everything. That's why we call it black, because you can picture light. If you absorb all the light, you would appear black. Now, that doesn't mean that it's not doing something. All matter actually produces its own energy. So matter produces energy, and here's why. I guess not produces. I think a better word to use would be emits. Matter emits or gives off energy. Matter is made of molecules, tiny molecules. Molecules are made of atoms. And atoms, of course, are made of charged particles. And so what we have in matter is things that vibrate. They shake around. And this shaking means that all of the little charged particles inside of atoms are moving. Vibrating, moving charge. Well, what does that do? Remember the big contribution of Maxwell. Wiggling electric charge causes electromagnetic waves, just like wiggling a cork on the surface of the water produces ripples in the water. So if you wiggle an electron, then all around it, it emits these almost magical waves in the electromagnetic field. So vibrating molecules or atoms produce electromagnetic radiation, which is another fancy word for energy in these waves. And of course, all matter vibrates. Now the cool thing is that matter vibrates a little bit differently depending on temperature. We also learned in grade 9 that faster vibrations indicate that we are having more rigorous vibrations, I guess you could say, indicate increase in temperature. Right? Increase in temperature. Or I guess more correctly, an increase in the amount of heat. Temperature is the way we measure heat, but measuring, of course, would cause it to go up. So an increase in the amount of heat. So heat is associated with the vibrations, and the vibrations are associated with the kind of energy that is radiated from all matter. So even a black body, even though nothing bounces off of it, it is something that just radiates its own energy. So basically, it would be, think about, putting something in a dark, dark room. You can't see it because it's not bouncing any light off. But if that object was radiating energy, say the object was warm, if you got close enough, you might be able to feel the heat coming off of it. So basically what we are able to do with a black body is we were able to analyze, we could analyze only the energy it emits. And that's important because that's what we want to find. We want to get rid of all the other energy that might be bouncing off of it that might confuse us. We want to know just how much energy there is inside this vibrating black body. Well, the original way of looking at this was to envision it as sort of a cavity, a space, right? Everything takes up a space. So these atoms are inside this space and they are vibrating, shaking around. So what that means is we get vibrations, we get waves, electromagnetic waves, which would be able to bounce around inside this black body. They would interfere with each other, and they would produce all kinds of wave combinations. But eventually, some of them would find their way out, and they would be emitted, and we would detect them. Now, the mathematical relationship that describes this, oops, I spelled that wrong, is called the Rayleigh-Jeans law. And of course, they're mathematicians and they scientists, and I'll just write this down because it's a good idea for you just to get familiar with the names. If you do go on in quantum physics, all of this stuff will become important. So these guys came up with a mathematical expression, and what they were able to do was they were able to show that, if something is radiating energy, the amount of energy that it radiates depends on the vibrations of its molecules, which depends on the temperature that it's at. So what this does is it relates the temperature of an object with sort of the amount of energy that it radiates. So the Rayleigh-Jeans law relates the energy emitted by a black body emitted by a black body to its temperature. So it kind of makes sense, right? And the Rayleigh-Jeans law looks like this mathematically. It takes something called B. Now you think of B as a magnetic field, but this is more an indication of the spectral radiance, how much energy is being given off. And we write it as a function of lambda. So this is like when you write f at x in math. It means that you're finding a function and x is the variable. Here we're going to find a function where lambda is the variable. And the equation doesn't matter. It's 2CKB, which is Boltzmann's constant. And this is the temperature. And then down here we have wavelength, and I think wavelength to the power of 4. We don't have to memorize this equation. What we have to understand is that this B, right, which is spectral radiance, and in fact what I'm going to do is I'm going to give it another name so we don't confuse it with our magnetic fields. The B, another way of describing that is called flux. So flux, and flux is something, if I give you a quick little review here, you'll remember that power is equal to the change in energy over time. And then you remember from your sound unit last year that intensity of a wave is, that's an I, and just my board is messed up here. The intensity of a wave is related to the power over a certain area. So it's power over a surface area that's emitting the wave. If you put these two together, what you get is energy over time and area, which means it's the amount of energy that's flowing through a certain area or flowing out of a certain space. So let's say you had this sphere and it was radiating energy outward, then the flux tells us the rate at which the energy is flowing out, so it's the energy over time, but also compared to the surface area. So really, we use this crazy word flux, and all it means is the rate of energy flow. Think of it like that. It expresses the intensity of the wave. Flux. And what I want to write here is that this flux is proportional to the temperature. You see how they're both on top, so if one gets bigger, the other gets bigger. Well, this is a very important statement. Since flux is related to the intensity, what this means is that intensity then should be related to the temperature. So that means that if the temperature goes up, the intensity must go up. Well, there's a small problem with that. If you graph it, you can kind of see it visually. Here's a graph of the Rayleigh-Jeans law. If you graph here flux, or you could put intensity, it's kind of the same thing, and you graph it with wavelength, you get this curve, which goes something like this. There it is. What it's showing us is that as wavelengths get shorter, the intensity of the wave should go up and up and up and up and up and up and up. Well, what does that mean? What it means is that right around here, we've got a problem because this is going towards infinity, which means the amount of intensity or the rate at which energy flows would become infinite at smaller wavelengths. Well, is this true? Does this happen? It turns out that with experiments, we can do measurements, and we can find out that no, that's not really what happens. When we do experiments, we find out that the graph actually goes like this. The Rayleigh-Jeans law works perfectly for long wavelengths, but as the wavelengths get shorter, it changes to something that looks like this, and it drops away, which avoids this nasty infinity where things get so big that, they're infinite. Well, that's a problem. Our math doesn't match reality. And that, in a sense, is one of the things that was causing this number one problem, where wave theory was breaking down. The Rayleigh-Jeans law is based on wave theory, and it produces a prediction that's not true for short wavelengths. Okay, well, that's going to give us some trouble, isn't it? The other thing that I should show you is that they were also doing experiments. Well, let me explain to you what happens when you heat something, just so you get the idea. Let's say you have a piece of iron. It's blackish iron. When you heat it up, it starts to radiate energy. Now, it's radiating energy all the time. The only way you can stop radiating energy is if you're at absolute zero where all your vibrations stop. However, if we imagine that this is very cold, it's still radiating tiny bits of energy. But the energy that it radiates will be of very long wavelengths, right? If you look back at this equation, you can see that the wavelengths of energy are varying inversely. So what this means, here I have written what happens with temperature. Well, because wavelengths are on the bottom, if the wavelengths get really small and go shorter and shorter, then the intensity, or the B, goes up. The radiance, the flux, intensity, whatever you want to call it. So it's a varying relationship that's inverse. Okay, so shorter, more heat added to this iron makes the waves begin to go from long. So first we have long waves coming out because it's fairly cold. As you heat it up, what happens is the waves that come out will become shorter and shorter and shorter. Now, remember our little spectrum. We have radio waves, we have microwaves, we have infrared, and then red, orange, yellow, and they get shorter as we go, right? So cold matter is emitting waves, but it's emitting waves way down here in the radio wave range that we don't hear or sense. Or perhaps it's not that cold. Maybe it's emitting in the infrared range. That's the microwave range, sorry. In the infrared range. Maybe it's emitting in the microwave and infrared range. The point is that it's making waves that are too long for us to see with our eyes. So nobody noticed this. And, you know, we notice the infrared a little bit. We can feel some heat there. There's infrared. We can feel some heat, but nothing major seems to happen. But something cool happens if you keep heating it up. It gets hotter and hotter and hotter, and suddenly it starts to turn kind of reddish. It starts to glow a dull red color. It's like, whoa, all of a sudden. And what's happening here is the atoms are becoming so energetic and vibrating so much that the waves they're producing are now in the visible light range. They're producing waves that are actually red light. All they did is get a little bit more energy. The waves became shorter in wavelength, but now we can see it. And so that is radiating red, as well as the other infrared and microwaves and whatever else. Now if you heat it more, then it will start to add orange and yellow to that, which means that this will start to look orangey yellow, and the glowing will begin to look orangey yellow. And that's kind of what we see, right? When we see something heated up, it gets more orangish. Well, then after that, if you keep heating it up more, the atoms will begin to vibrate even more, and we will get the green and the blues mixed in. And if you mix all those colors together, well, then you get white. So what happens is the object begins to glow white. White hot, we say. And so this is what's happening. All of these wavelengths are being emitted from the iron as it heats up. If you kept heating it up, then you'd be able to produce even maybe ultraviolet rays that would come off of the iron. Then things get weird. For some reason, ultraviolet, right, which is the wavelength that happens right about here on the Rayleigh-Jeans law, this is where everything goes wacko. It turns out that it doesn't follow the same rule. Everything gets different. And we're going to show how that was fixed very soon. The other thing we should notice is that if you take a pure substance, like a piece of iron is great, but it's got lots of impurities in it. Let's take a nice pure substance, a pure gas, and heat it. Well, we should see the same thing. As we heat the gas, it should emit all the different colors, and it should make this kind of behavior. But here is a picture. Let me see if I can get to my internet here. Here's a picture of the atomic spectra of certain elements. You've probably seen these in chemistry. Look at the top bar. It's the whole spectrum. That's kind of what we would have expected as we found hot gases. If we took sodium or hydrogen, let's use hydrogen, it's the second one. If we were to heat that up, we would expect to see that it would emit light slowly from the red end, and then more orange, and then more yellow, and then more blue, but there shouldn't be any gaps. But of course, this is not what we see. We see hydrogen only emits light at 4 very tiny specific places. Somewhere, the red line between 7 and 600, and then just around 500 there's a green line, and then there's 2 blue lines, and that's it. Why the heck does hydrogen not emit light, say, around 680 nanometers? Why doesn't there any light at 720? Those black spaces mean that no energy is being emitted. Why doesn't the heating hydrogen look like the top band? Well, that's the problem. Our wave models tell us it should look like the top band, but it doesn't. And so we have an issue. Now, how we solve that issue is a little bit interesting. The solving of this issue occurred when a certain person who wasn't even trying to solve this problem at the time, his name was Max Planck. And he's the first guy that we'll talk about. We'll just discuss his contribution, and then we'll move on. What he was working with light bulbs. He was trying to find a way to make light bulbs more efficient and work better. And that's what his job was. He was a researcher trying to figure this out. So, how do you make better light bulbs? Well, interestingly enough, what is a light bulb? A light bulb has a filament inside. It's a little thin piece of metal. What do? We pump electricity through it until the resistance causes it to heat up. If it heats up, its molecules begin to vibrate, and they emit radio electromagnetic waves, microwaves, radio waves. And if they heat up enough, we can get them to produce red waves and orange waves and yellow waves, and voila, we have light. So all we need to do is get enough energy in there to get those wavelengths. But he was trying to make this improve. And so basically, what's a light bulb? Well, in a way, a light bulb is like a black body. It's pretty much emitting most of the energy that's involved with it. Very little is being reflected. So in a way, Max Planck was investigating black bodies. And so he was looking at some of this math and some of these things that we've discussed, and of course the Rayleigh-Jeans law, which doesn't work, and he came up with a fantastic idea. He said that what if energy isn't allowed by the universe to be any level? He basically said, what if energy only comes in packages? It's such a simple thing, but it made immense changes in all of the physics. Let's think about going to the store. In the days before you had the bulk barn, but I guess even then we could use the analogy. Let's say you wanted to buy some sugar, right? Well, you're not allowed to buy as much sugar as you want. You can go to the store and you can buy maybe a 5-kilogram bag of sugar. You might be able to get a smaller bag, 2 kilograms, right? Maybe you can find those little packages that you put in your coffee, little tiny packs, but which would be just a few grams of sugar. But if you want to buy 2.73 kilograms of sugar, you can't. Nobody sells that package. It doesn't exist. Even if you go to the bulk barn, you say, oh, at the bulk barn, I can pull out as much as I want. Well, then let's take it further. Let's say you wanted to buy one little tiny crystal, I should say, of sugar. One crystal. You picked one crystal of sugar out of the bin, went to the cashier and said, this is it, please. She'd be like, well, that's weird, but okay. What you can't buy is 1.5 crystals. You got to buy 2 crystals. And even well, let's break the crystals apart. Okay, well, then you can only buy 1 molecule of sugar. 1 molecule. You can't have half a molecule because if you break the molecule of sugar, it's no longer sugar. So there are limits to how much sugar you can buy. You can't buy 1.5 molecules of sugar even at the bulk barn. And so the idea that things come in limits or come in packages is pretty common. What if energy works the same way? And this is what Planck did. He came up with a way of describing how energy could be quantized. Now that word is weird, but not really. A little package is just an amount. And another word for amount is just a quantity. And so he came up with this idea that there would be little quantities of energy, and he gave them a special name. Using this language, he called them a quantum. 1 quantum, or if you want the plural would be quanta. Quanta. 1 quanta or 1 quantum.
Hey guys.